All right, so here we have data sets and features. We have a machine learning. So I keep saying this, throwing this word, pipeline. Right, and I keep saying the machine learning pipeline. All right, so usually whenever you take a machine learning course, it's kind of the first thing they tell you about, right? So because you want to learn how to frame the problem. You know, it's usually going to be an abstract thing, right? And so like his problem of radio signal detection, right? So, okay, that gives us something, but how do we start putting all the elements together? And so the first thing you want to do is, okay, what's the data? You know, you said, right? So you were using some tool that allows you to extract the data and putting it in a folder. Okay, so we start check, I got that. Then what else do I need to do? Well, usually what you have with data is that it's messy, right? So you need to clean the data. And this is usually referred to as pre-processing also, all right? A lot of work goes into that pre-processing. All right? Then, once you do all of that, you need to convert your data from whatever it is into what is called the vector space model. All right? So that's kind of, there's a lot of terms for this. I usually just like to call it the vector space model. It's very important that everyone understand how to do this, all right? To go from here to there. Because the great thing about this is that once you know, for instance, you could misunderstand your problem, right? That could be, I'm not saying you did, but that could entirely be possible that you're just not understanding your problem, and so you can still convert it into the vector space model, but it's not correctly done, and so your results are not going to be what you're looking for. That can happen. All right, and so a lot of work goes into this area. All right, a lot of work goes into this. Understanding my problem, getting my data, labeling my data, remember cats and dogs, cleaning my data, getting rid of things that are unnecessary, and then finally arriving at the vector space model, which is X and Y, right? So let's think of it as an X matrix and a Y vector, all right? So this is the data that I'm trying to collect. And don't worry, this is one of the most important things that I definitely want to make sure everyone understands by the end of this week. So think of today's quiz, for instance, it'll probably be about this, right? So it'll be, giving you some problem, and I'm going to ask you, okay, and the answer might be different for everyone, right? And it doesn't mean that it's wrong. It's just your interpretation of it, right? So, but you need to arrive from whatever raw data you have into the vector space model. And this usually has some statistics. So that means there's an N here, there's an M here, right? There's sizes for this matrix, right? Number of rows, number of columns, what are the values here, etc. Everything needs to be aligned properly. And then here in the Y, you have the labels, the supervised or unsupervised part. Does this make sense, guys? Another term for this is feature engineering. Feature engineering kind of goes to that problem of radio signals, right? Radio strength might be one thing. May I ask you, what are like 3 features that you look at in your signals right now? 3 things. Power gain. So you have, okay, so the signal is an interval of time, like every second, an interval of 1 second, right? And you got the frequency there, and you extract that, right? All right, so that's important because that's the first thing we need to define in the vector space model here. Each row is what is called a sample. And you need to define that. So that could be one packet, for instance, in a network. But a more difficult problem is usually what you have, an interval of time. Because with a radio signal, right, it has to be, I say something 1 second, and the next second, and the next second, and you have, radio frequency looks kind of, some kind of, a lot of signals there, right? And so you need to extract information from that. So the first thing he did, without us really being electrical engineers or anything like that, is to figure out what is a sample. So in his case, Dan's case, is a 1 second. So that interval of time defines one row. You see that in the vector space model. That 1 second is one sample, the next second is another sample, the next second is another sample, and so on. So he's already defined part of the vector space model. Then he needs to decide, okay, how many hours of these signals do I have, right? That's going to determine how many samples he has. So the n there. And we still haven't even looked at the features. So the features are usually going to be the columns up here. All right, and he said, I think, power gain, that's one feature. And so those are basically just some value, right? Some metrics, right? So the next question will be, how does he get from this, right, from that signal, how does he get one of those? Give me an easy one to say. So it's an angle, okay, of the antenna, right? So the angle, so like 90 degrees or something. Okay, so there you go, right? So for that 1 second that he established already as an instance, right, a row, now he takes azimuth, right? That's a feature. And then what is the value that he takes? The angle of rotation. So let's say 90 degrees. So that's what would go here. So this one is 90 degrees. The next one might be 60 degrees. The next one might be, 180 degrees, right? Do you guys see that? Oh, the movement is too fast. Yeah, I don't know the domain, right? And that's another thing. So the person that does that's a very good point. All great points. So the feature engineer that does this obviously understands their data, right? And I'm just making things up here, but what the algorithm is looking, going back to what you're saying, so 92, 91, right? That's more consistent with the data. Now, if you see something like 180, and then if you look at the labels, and the labels are 1, 1, 2, what do you think a machine learning algorithm would learn there? Not if what? Oh, no, I don't know if maybe I'll make this bigger. Maybe that's what it is. So, we're looking at his example. So 90, 92, 91, and then I have a 180 here. So when I write this, what do you think an algorithm learns?
The last sample is in category 2.
Yes. Why?
It doesn't match the pattern.
Of the pattern of the ones. What is the pattern of the ones? 90, right? It's in the 90 range. Exactly. You see that? That's what a machine learning algorithm is looking for. If your data has zeros here, but those zeros are just missing data, so it's not that it's an actual zero angle. It's more of a missing data. This is a problem. No, but it's a good example, though. It's I don't think we're wasting time on his problem. I actually think it's really great because it's really taking us to that vector space model, which is where you want to arrive. You want to understand your data. You want to understand it so well that you kind of have an intuition of what the machine learning algorithm might do. All right, but in a nutshell, that's basically what we're looking for. Correlations. It correlates these values to these values. So if I see a whole bunch of 1s and 90s, I start to learn that. If I see it, this was a 2 and a 180, it starts to learn that higher angles or whatever, southern angles or whatever, are associated with 2. But you really don't want, you can, but you don't want to have missing data. Because if I have zeros here, what do you think machine learning will learn? That it's a valid value, right? It is a valid angle, right? It's north, right? So it'll learn that, and that's not correct. This could have been 75, but because it's missing data. So that's one of the issues that we want to address. All right, but anyway, so the whole process is to go from understanding the problem to the data and then to the vector space model, modeling it. Once the vector space model is clear and understood, then we can do 2 more boxes. which are the, let's do a circle actually, the machine learning algorithms that we apply, right? So something, we decide supervised, unsupervised reinforcement learning, right? And we build a model. So this is where you build a model. Right? So you build a model here. And then finally, you analyze the performance. So we're going to learn things like the F measure, F1 metric, or accuracy. All right? So this, in a nutshell, is machine learning. That's the machine learning pipeline. And this is the thing, the whole process. Today we're going to focus just on the very first part, getting to the vector space model. All right? Questions? Any other questions? All right. So, so as you can see, the learning outcomes here will be feature extraction, etc. So data sets is also, important, right? So it's data is king, as they say, right? There it is. I even wrote that. Data is king. It's usually one of the challenges. So, in academia, for instance, I've said this, it's very hard to get like the real data sets, usually companies, I have a friend who works at Blue Vector, this company that does machine learning for cybersecurity, and what they do is they basically specialize on going to like banks and healthcare organizations. So they have access to their data there. And so they take that data and they make specific solutions for them, right? Based on what they have, they build machine learning algorithms that can, detect various things. But if you don't have the data, it becomes a little bit challenging because you always want things to be specific, right? So you want your solution to be specific to the problem or to the data. So you don't want, for instance, to take just some standard intrusion detection data set, build a model, and then apply it to some bank and expect it to work. So it doesn't kind of work that way. Instead, you want to have specific solutions. So data sets are central to machine learning. The algorithms are data hungry. So what that means, especially like deep learning and other algorithms like that, they really need a lot of data, all right? To actually, people always say this, that's why machine learning is not actually true artificial intelligence or human intelligence, right? Because humans really just need 2-3 examples and we learn, right? So it's like a little kid walking and falling on something, right? If a kid falls once or twice, they're going to learn not to do that again. A machine learning algorithm can't learn from just 2 or 3 examples. It's basically, the analogy is it has to fall 1,000 times before it actually starts to learn, if that makes sense. All right, so the algorithms are data hungry. You need a lot of data. So what is better to have? The most powerful machine learning algorithm and small amounts of poor data, or lots of data, even if our algorithm is not the best. And this is something I was saying before. This is the better one, right? So you can have deep learning here, but terrible data, and it's not going to do very well. Or you can have really great data that you understand really well, and just some basic algorithm like KNN or some standard one, and it'll do okay. Okay. So data is king. So what makes companies like Facebook and Google do so well then? We're always hearing, right, that Google and Facebook are always innovating. Amazon, they have Alexa, and why is it that, let's take Alexa's example. Why is it that Amazon's Alexa is so great? Let's say that you're very smart and you build your own Alexa. What would be the difference between you and Amazon? And why do they do it? Because of what you just said. Because the more data you have, the more examples you have about something, with some context, right? They might know the time of day, they might know something about what's going on in your home, and so that's the labels as well. So their algorithms just get better and better, right? They follow what you shop and they tie that to what you're saying, and they somehow figure things out, right? So this is what separates one person, doesn't matter how smart they are, from these companies, is that these companies have tons of data to learn from, right? So And so that's why data sets are so important. That's why, you know, people always say, oh, we need to do big data, because they need to have all that information to learn more, to learn better, basically. Are there any questions? So anyway, so I was talking a little bit about that pipeline, right? So, you know, remember the pipeline, data, and then the vector space model. Oops. So the first thing that I want us to learn about is this, the vector space model. Right? So kind of right now, I want to take his example actually, Dan, if you don't mind. Can we do that? And we can all we have like 15 minutes. So I'd rather we do that, take a break, and then we'll continue with the slides. So I just want to go with this. So I like the fact that it's like an abstract problem. So let me create a slide here. Oh no, I'd rather just pick your brain. So I have the expert here, so that's definitely all right. So again, this is, you know, as I said, one of the most valuable things. If there's like 3 things you can learn from this class, this is one of them. That's really important. All right, so we'll just do a little exercise. So vector space model and data, right? And then at some point we'll do machine learning. So again, several things. All machine learning algorithms need data sets in a specific format. All right, that's the first thing. So let's think of something easy. Let's think of plants, right? What is called the Irs Data Set, right? The Irs Data Set looks like this. All right, and this is X, a matrix, uppercase X, and a Y vector for the labels. Right? This will be a supervised learning problem. So I'm defining that already. Supervised. Okay, that means I have labels. In fact, I have 3 labels for 3 plants. All right, these are called Setosa, Virginica, and Versicolor. Just 3 plants. All right. So I need to differentiate between these 3 plants, right? So what would be some features that I need for differentiating between plants? Like if a person observes a plant, how does a person know the difference? They're kind of within the same species of plant, so it's not like a pine tree and like, you know, flower bed or something. It's more alike. So what would you say? Color of the leaves maybe, right? What else? Stem length, perfect. What else? One more. The what? Leaf shape, right? Exactly. So those are the features, right? So stem, shape, and color, correct? Now we don't want to write all of this on the matrix, so let's just call these F1, F2, F3. You see that? Pretty simple. So we do F1, F2, F3, let's say F4. So F4, just so I keep it consistent with Iris, something with the roots, right? The petal. Somebody said the petal. Yeah, something, right? There's some shape, but it's a metric, so it's a length, right, or something like that. So now we have F1, F2, F3, F4. You see that? These are the columns that our data set needs to have. So think of this like an Excel spreadsheet, basically. Think of it like an Excel spreadsheet. All right? Now, what else do we need? We need to define what a sample is, right? So in our case, this is very easy to define. It's just a tree, right? One tree here, one tree there, one tree over there. That's the sample. So we need to define what a sample is. So in this case, it's a tree, right? And so now 1, 2, 3, 4, 5, oops, and so on. We have 5 trees. And then, you know, we have different categories, right? So let's just use numbers. So 0, 0, 1, 1, 2. Do you see that? This is what I just created here is a data set that's perfect for a machine learning algorithm. Now these values here should be numbers. So it should be like 2, 2, 4, 4, 5, or it can be 0.01, 0.02, but you don't want to have words. You don't want to have like L and R. You don't want to have that. So if you do have that, you're going to encode it into a number, right? So if you had a lot of like L and R, just make it zeros and ones. Does that make sense? And that's it. So this is what you want. So I started here because that's what you want to arrive at. Once you have this, you can just feed it directly into a machine learning algorithm, and it's going to make sense because you have samples here, which is this, the rows, right? We've defined a sample to be a tree. We have features, which are the color, the stem, the shape, the roots. Now, how did you identify those features? Because we all know what a plant is, right? We all have seen plants before. So that's why we can do this. And then the labels, we just identified that we had 3 types. That's somebody that knows anything about trees, botanist or something, so they can identify, oh, this is this type of tree, that's that type of tree, and so on. And so now the machine learning algorithm can start to learn the subtle correlations, right? All right, so that's what we want. That's what we want. So we want to go from a lot of raw data to arrive at this. So now let's look at Dan's problem. So let me create we're going to repeat this, but now in that context, if you don't mind. So your data, right? So where do we start? Let's start. We want the vector space model. So we want X. We want Y. And we're just going to start to put it together. All right, so what can you tell us? So those are the features, right? So the first question I would ask is, how many features do you have? 34. Okay, that's not too bad. So you mean they're like, they correlated with each other? Yeah, so it's like if it's, so winter, 32 degrees, summer, 85, right? That's what you mean, right? So they're correlated. So they're actually there, you only need one of those, right? Because if it's always going to happen in correlation, right? So they're like, they're not in, linear regression, right? The dependent variable is linked to independent variables. That's kind of one of the assumptions. So here he's got 2 that are, so you might get rid of those. All right, so anyway, so this is how you do it, right? So this would be the first part of the problem. Go from raw data to this. So we already identified 34 features. What are they? Just give me like a couple.
Yeah, so we'll do elevation.
Elevation. Oop, yeah, elevation.
We'll do azimuth, which is pretty much just a circular angle.
So I think that's like that. What else?
Let's do decibel level for power.
Power, the signal strength?
Yeah, power gain.
Power gain, okay.
And, wind speed.
Wind speed.
And
Oops. That's good, so that's enough. But so this is where your expertise comes in, right? So you know what these are. Now, what are the values that you would associate with these, like elevation, for instance? So it's angle. All right, so it's something from 0 to 360. Okay, 0 to 360, okay. In knots is like, so from 0 to 70 miles per hour, and then decibel level. But it's just like a number. Is there a range? Let's 0 to 100 maybe. So 0 to 100. So there you go. That's the features, right, that he identified. And so now these features go here, F1, F2, F3, all the way to F34. Do you see that? Now, how many samples do you have, would you say? But first of all, what is a sample, right? That's what we had. So in our previous example, a sample was very easy, straightforward. It's a tree. Or in the one of the cats and the dogs, it's just a picture of a cat. That's it. And then another picture of a cat, right? Pretty straightforward. But here, this is a little bit more challenging, right? It becomes a little bit more abstract because it's an interval of time, correct?
yeah, time series.
So let's say that how does it work? You have a machine that's recording all these signals, 10 years of data. It's all like a signal, right? So looks something like this over time, right? This is
Yeah,
time. All that, like basically like speech almost, right? So if it's like, this is frequency, correct?
Yes.
Okay. So this is 1 second, and then 1 second, and so on, right? So that's what he defined. I don't know why. That's your decision. Is there any criteria why you decided 1 second over 2 seconds or?
Yeah.
All right. So then that's, he defined each sample as a second. So each row here is a sample. All right. And that's what's important here. So then let me just S1, S2, S3. And so you said there's 10 years worth. So that's probably a million of these, or
Oh, it's way more than that.
way more than that.
Yeah.
Okay, so SN, let's say, right? But as you can see, that's what a data scientist would do, right? You know, start to analyze the problem, break it up into parts. So a sample is a 1 second interval. Do you have the signal itself or just these numbers?
Yeah, so to give an example, like there's a 70-meter dish in California that does this, right? So you have like dish would be tracking, let's say, well, just to keep it simple, one spacecraft, and the columns between that, the rest is the data. So spacecraft has the data, and the antenna at California has data. It's like wind speed is hitting that. This wind speed would affect the signal columns between the spacecraft.
Right, but what I mean is you have these values like the elevation, azimuth, etc. But you also have like the actual frequency.
I do.
Okay, you do have that.
It's just a floating point.
Okay, because if you have this, you can. This is the like the frequency domain, right? So you could extract some things from this.
Yeah, so there's like S-band, X-band. Like NASA has specific bands with the space committee that only they do.
Okay, all right. So there's more features. What I'm saying is there's probably more features to extract. I would think, right? It's like in math, if you have a signal like this, you can take like from the time domain to the frequency domain, so the Fourier transform, yeah, all that stuff. But you're not using any of that.
Yes and no.
Yes and no. Okay. So anyway, as a feature engineer, he could. Is it 10 o'clock? All right. Oh, all right. So let's take our 15-minute break, and then we'll come back to your problem and finish it up. As I said, this is a pretty important thing. All day we'll be doing pretty much this. Okay. So let's take a 15-minute break. So I'm going to do from now until about 11. Just continue this discussion of features and data sets, finish up these slides, finish up kind of his problem. Then from 11 to 11:45, we're going to look at Weka, right? So I kind of want to get you guys to that. That will give us the whole pipeline, all right? So we're going to look at the entire kind of pipeline. Also, Tingyu was telling me, did everyone get a flash drive? It seems that maybe a couple of people didn't. Everyone did? Okay, great. So that's the plan, right? So we're going to do the slides here, and then we're going to do the Weka program, kind of go over that. Then we'll have a short little quiz, just kind of give you a problem, create the vector space model, basically. And then we'll have a 1 hour and a half for lunch break, right? And meet back at 1:30. All right, so are there any questions before I continue? All right. So, all right, so this is what we were doing. We were analyzing how to go to the vector space model. So the best way to know where to get is to kind of see it first, right? So that's why this is Iris. It's famous Fisher's Irs Data Set. All right. So that's what a supervised learning featured data set looks like. You can see it here. So we have the samples, the features, the classes. Then the radio signals problem, right? I think that's what we're doing. Radio signals. All right, so it's a data set, really large it seems, millions of records. we've already so remember, when you're thinking about this, you want to get to the vector space model. Now, there's a lot of steps that can go into this, right? But you want to start building it. So we identified that the signals are 1 second. That's, remember, is the sample. Okay? Each sample, 1 second. Now, what happens if you had signals of 1 second and then you have other signals of 5 seconds and then you have a signal of 1 minute and then a signal of 0.01 second? What do you think about that? Is that something you kind of want, or why or why not? Right, exactly, right? It's like you want to compare apples to apples, right? So that's why people always do that. So if you think, for instance, when we were going back to that example of cats and dogs, right? You don't want some images of cats to be really big and some to be very small. Also, you really don't want cats to be here in the left in some images and then cats in the bottom in other images. You kind of want all cats kind of in the same place, right? Centered maybe. I mean, that's the optimal, perfect world. Now, you may not always be able to achieve that, but that's kind of what you want. Because as he said, right, you want to compare, you want to be consistent in your comparisons, right? So in here, you know, in 1 second, you might have just a specific pattern that takes place, whereas if you do it in a minute, there might be multiple things that might be happening to that signal. All right, so that's one of the first things, right? You want to decide in something consistent, so 1 second intervals. Then you identified the features, which are these 34 features, all right? Then what about, and then you know the values, right? So you know the values are 0 to 360 or 0 to 70, right? Yep. All right? Now, why do I call this the vector space model? Why? What do you think of when I say vector space? What would you say? What?
Linear algebra.
Linear algebra. All right, yeah. Perfect. Perfect. Linear algebra, right? So a space. So let's do here. So this is also an important concept. So somebody said, I think, that algorithms are algebra, and then machine learning is linear algebra, right? So it's kind of like that, right? So the vector space, what we were doing before, is really creating a space. So let's think of the simplest one, right? Cartesian space, right? So we always know this as x and y, correct? That's kind of how we learn it in school. But as it turns out, these are the features themselves, right? So this is f1, this is f2. So the features that he mentioned before, elevation, let's just take elevation and wind speed, right? Elevation and wind speed. So f1 is elevation and f2 is wind speed. Right, and this was from 0 to 360, I think, and this was 0 to 100, correct?
Yeah, it's fine.
All right, so what does that mean? You know, the fact that this is x over here, f1, f2, and this is 1, 2, 3 to n, and the labels we're not really concerned with right now. So that translates into plotting this here, right? So f1 is elevation, so that means it goes from 0 to 360. Do you see that? And then the next one, wind speed, is f2. It goes from 0 to 100, right? You guys see that? And that's what, you know, vectorizing this or converting it into the vector space model means, is that you take your data, however it is, and you're plotting it in a vector space. Why do we want to do that? Why would you want to do that, would you say? Do you think? No. Why would you want to, now that I have that nice little graph there, why would you want to, yes sir?
If you plot it out, you can start to see
Perfect. Exactly right? That's exactly right. So for instance, you know, I have one sample here, right? And one sample is, let's say, 20, and these may be wrong, but I'm just making this up. 20 and 20. Do you see that? And then the next sample is another second, might be 180 and 178, right? And then a third one might be 270 and 280. Do you see that? So now I can plot this, right? I can plot this. So that's why this is so important, because once you put it into a Cartesian space, you have Euclidean, right? What is the other thing? Pythagoras, right? We all know about that. And so that distance of triangles, right? And that's the thing that you get in there. The ability to calculate distance metrics, for instance. Right? So the ability to calculate distance metrics in that space. The ability to group. The ability to separate. Right? So now we know sample 1 is 2020. So that's going to be around here. S1. Right? Then I have S2. That's about... Oh, wait, hold on. I have an error here. Sorry. So this should be, right? F2 should be what? Something in the range between 0 and 100, correct? So let's say this is 80, and then this one is 90, right? Yeah, sorry, you know. But good point, right? So these are the values. So the second one is 180, so it's kind of in the middle, and 80 over here. That's S2, right? And then we have the third one, which is 270 about here and 90, S3. Do you see that? And so that's what you get by creating the vector space model. And the great thing about this is you can do this for any problem, right? It could be a language problem, you know, classifying books from Shakespeare or, you know, French literature, whatever you want. Still works. Images of cats and dogs, still works. Network data, still works. Malware, you know, whatever, phishing problems, whatever you want it to be, you know, radio signal detection, right? You can always do this. Does this make sense to everyone? Are there any questions about this? All right, so that's all great and all, but what happens if I have 3 features? So decibel, I think it was one of 0 to decibel.
Negative 121.71 dBm.
That's the range?
That's what's currently at 1 second.
That's the value there.
Value, yeah.
But the value might be within a range, right?
Yeah, say plus 50, minus 50, that. Yeah, I forget.
So let's say minus 150 and I don't know, 250. Let's just make it all positive to not complicate things. Kind of like that. So it's always within that range, right? So how do we add this one? Well, 3-dimensional, right? We had a third dimension, that's F3, because what happens is when you create, you know, mathematically, people will say things like, you know, orthonormal or orthogonal, or they'll throw in, you know, any of you that have strong math backgrounds will probably know that term and, you know, understand that it's very important. Here, I'll just say that it's kind of like, you know, what we know. In algebra, it's 90 degrees, right? So all these new axes that we're creating are adding to this vector space are at 90 degrees from the other one. So we have one line, then another one, then another one. And mathematically, if we even added a fourth line, a fourth axis in a hypercube, that would still be not 90 degrees necessarily, but orthogonal, right? So it meets that mathematical condition, which basically means that the math holds as we start expanding this dimensionality, right? And so, but anyway, we don't really have to understand all that math, right? We can just understand the intuition of it. And the intuition of it is we are modeling it on a vector space. All right, and so this decibel, okay, so here it's always going to be like within 150 and 250. Oops. So we're not really going to use maybe this space, but we can ignore that. Right, and still started at from 0, let's say, to 250. Do you see that? So that's what's happening here, right? Oh, yeah, good.
Basically, you have to know your data enough to know what features have strong correlations.
You kind of want to know your data, but sometimes you can just give the algorithm your data, and we're going to see when we do the WECA lab that you can do like a feature ranking kind of thing, and it'll tell you the contribution of the features, for
But
instance.
if you're trying to plot something in
Yeah.
terms of the two-feature thing, to see clustering, wouldn't you want to know that those two features kind of go together to make a cluster? I mean, you don't want to cluster around something or get randomness in your plot.
Right. I mean, this is the data that you collected, right? So what you're doing is you're viewing it in just 2 or 3 dimensions. Remember that we can't really see it in higher dimensions, first of all.
Right.
And you're almost never going to be able to view your data, I guess is what I'm trying to say.
Right. I'm just saying if you had feature 2 was temperature.
If feature
you
2,
don't
if feature,
know anything about your data. I mean, that you're trying to
say that again, I'm sorry. If feature 2
If
is
you had a feature was like temperature.
temperature.
You wouldn't know that really had anything to do with.
I see what you're saying. Yes. I understand. So F4, let's say, is temperature. But for his problem, radio signal detection is irrelevant, is what you're saying, right? You can still add it, would be my answer. Because while temperature might be obvious, azimuth 37G, I don't even know what the azimuth part meant, right? And so I can't really interpret it, is my point. But you're very right. It may have no bearing on this problem. But that's one great thing about the feature ranking part of machine learning, is that it can tell you that. What we're going to learn actually very, very soon when we do the WECA lab is that we can actually do what is called ranking the features. And it's going to take all features from 1 to 35, and it's going to say this one has this contribution, and then maybe at the bottom it'll have 10 that just have a 0 value, including your temperature. And at that point, you know that you can just get rid of that one. And then so we go and we delete it. Does that make sense? Is that what you were getting at?
Yeah, I'm just saying if you're taking 2 features to plot them and say, okay, these line up over here as this category, and these line up.
You're saying if this was temperature, for instance.
Right. It might not necessarily plot the way you're
Yes.
actually want to.
So
Bin them.
I completely understand. So what I would say is don't plot it first. First rank it, get rid of the ones that are useless, and then plot it.
Right. Okay.
However, I will say that plotting is not something, it's unfortunately something that we can never do in machine learning. It would be so great if we could, but we can't really. And here's the thing. I drew this just for your intuition, for you to understand the vector space model. It's 2 dimensions, we can plot it. 3 dimensions, I can plot it. What if I add that 4th dimension? Can't plot it anymore, right? That axis is orthogonal, which means it's like a 90-degree thing, right? That's perfectly fine. The Euclidean distance metric, Pythagoras, and that triangle formula that we learn in high school, that still holds in 4 dimensions or 10,000 dimensions. No problem. The math holds. Unfortunately, we can't visualize it anymore. Not all the data. There are techniques to visualize a compressed version of the data. We will learn about that on Friday with something called singular value decomposition. Yes, sir.
Also, principal component analysis, PCA.
That's the same. Not the same, but similar to singular value decomposition. Yes, what you just said. So what is he saying there? What he's saying is, I have so he's saying PCA, right? So as I said, I will provide an example. Hopefully that'll make sense. But what is this PCA or SVD? PCA, or singular value decomposition. Oh, I'm sorry?
Principal component.
This is principal component analysis, correct. And it's a technique. It's a compression technique for data. So what happens there is that you had F1, F2, F3, F4, right? And then you're going to make a linear combination of those given some weight. So now you have P2, P3, P4 of the same ones. And so on, right? So you make a linear combination of these, the same n here and n here. So you might ask then, what is this good for? Well, what's good about this is that you might have here, let's make this actually n. But the algorithm has an objective. And the objective is to capture as much of the information in as few of these as possible. And so that's the trick about this, is that you're kind of trying to map these to the data, to maybe just 3 dimensions. Do you see that? So that allows you, whereas here, this might have been 10,000. You can't plot that because it's too big, right? We can only see 3 dimensions. You can plot all 10 into just these 3 principal components, and now each sample can be plotted in a space. So that allows you to visualize the data. However, it's not always, it's always so overlapped. I actually have some slides where I did this. The data is so overlapped that you don't really get much out of it. But that's what that technique is for. Does that make sense? It's not it's still not a visualization tool, I would argue. It's more of a tool for creating matrices that are smaller, which basically means that they require less RAM memory. So that make it more faster to process on the computer. But they lose some information, etc. Does that make sense? Okay, so that takes you. So it's a way of compressing a space that is the orthogonal thing, 90-degree angle of multiple dimensions, and you map it into maybe just 2, so that you can visualize it, compress the data, etc. On Friday, we will do an example of this. Not for plotting necessarily, but just for seeing that we can take a lot of features and reduce them into just 2 features. All right? Any questions about this? All right, so as I was saying, machine learning is linear algebra, right? So it's a lot of that linear algebra. And so you want to think in terms of the vector space model. This is one of the most important concepts in this whole class. All right? So now I'm going to go back here. So this is what I was doing. So I'm creating, his problem, the distance metric, or the radio signal detection. I have some features, elevation, wind speed. These are plotted here. As I start adding new features, I start adding, extending the dimensionality, it's called, right? So you go from R2, R3 to Rn. And although you can't view this Rn, the important thing to always remember is that the math still holds. So this Euclidean distance, for instance, still holds, and so on. All right? Now, so hopefully that makes sense, right? But I want to go back to just a simple 3-dimensional. So remember, we were plotting the samples, right? S1, S2, and S3, right? So those are 1-second signals, I believe, from. So now this is where we need to understand your problem. So what are those again?
The ones I said before?
Yeah, that 1 second. What are they supposed to give you? So now, because our Y is empty. You see that?
Yeah, so it could be 4 things. So it could be a carrier signal, which is hello, just kind of making sure it's there, on track.
Is that what you're trying to classify, or what you're trying to model?
Yeah.
That I get this. So my question is, I get this signal, right?
Yeah.
This 1 second signal. Now, what do you want me to tell you about it?
Yeah, so I can do the real answer, or I can make it really simple for the class.
Very simple for the class.
Yeah, so let's just say it's a command signal, you're sending it to the Curiosity rover on Mars to move.
Okay.
Yeah.
And is there a limited set of commands that you're sending?
Yeah, I'm pretty bad at that stuff, but yeah, I would
Okay, so that's what you're trying to classify, is the command, right? Command 1, or command 2,
Yep.
and maybe a command 3.
Yeah.
Because if we have 100 commands, that changes the problem entirely, right? So it's a supervised learning with 100 classes. That's much more difficult to do, right?
That's pretty much what I have here.
Okay, so let's assume that it's just 3 commands. So he gets the signal, and you want to identify if it means C1, C2, or C3.
Yeah, and C3 could be loss signal, for example.
Loss signal.
Yeah.
Okay.
Drop signal.
Okay. So basically that's what it is, right? So we identified the classes, all right? So how can we identify that in the vector space? Well, somebody said, first of all, if we didn't have these, we have no way of understanding the difference between S1, S2, and S3, correct? We have no way of understanding anything. But we plotted these in a Euclidean space. So we already know a little bit about each one of these, right? If I asked you to create, for instance, 2 groups here, how would you create them? For those S1, S2, and S3. 2 groups. That means put every sample in a group, but you only have 2 groups. So how would you group it?
S1 would be one group, and 2 and 3 would be the other group.
Do you see that? That's some machine learning right there. And you didn't have labels. No labels over here. This is the part that's called unsupervised learning. And that's what we'll learn on Friday, is something called the k-means algorithm. Do you see that? All right. That was unsupervised. Now let's go back to supervised. So in supervised, we had 1, 2, 2. Right? We have 1, 2, 2. 2 classes. So that roughly translates into this being a 0, this being a box, this being a box. Right? So it's, it's just a way of me labeling these now. Okay? Or actually, I don't want you to think that I'm creating a shape there, so let me... Okay, so instead of... Let me just... So this is S2, S3. You see that? That's the equivalent of supervised learning, is that now you have the vector space model, and you have the samples in there. You have the samples in there, but the S2 and S3 one is blue, the S1 is red. So that's, one is labeled, here is red, and these 2 are labeled as blue. Okay? So now that's different. That's a different problem, right? So now we know more about this. What we want to learn here now is, how do we separate this data? All right, so we want a rule in this Euclidean space that allows us to separate the data. All right, and what that means is, maybe we want to create a function in this space that allows us to separate the data. Now we learn this simple equation in school, right? Y equals mx plus b. Right? Oops. That's the formula of a line, right? You remember that, the formula of a line. So you need to have the value of x here, right? So let's say that one, and you multiply it times the slope plus a bias, and then you can identify this, write this line, right? You can draw this line. This formula is pretty much everything in machine learning. And that's it. That formula, that little formula does everything. And so now what we need, so if I know this, that I can draw that line with that equation, okay, I know a lot. Because I know that I can draw a line in this space, right? That this same line I can draw there, correct? Pretty much. If I have that, now what do I need though to draw this particular line in that space? What values do I need? F1 and F2, but in the context of this equation, because F1 and F2 are x values, right? So they're that actually. I need, you mean to create a point, you mean? Right? That's what you mean? Yeah. So so remember this equation. I give it this x, which is this x, and it predicts this y, which is this one, right? So that's basically what you're doing there. You're drawing this line on here, right? But the thing that you need to learn or understand to differentiate between that line and that line is really what? The parameters, m and b. Does that make sense? I mean, I can say this again, but this is important. Once you understand this concept, that's pretty much it. Everything else is just like complicating this. But now, so it's y mx plus b, right? So again, remember, I give it 1x, this value, which here our x is f1, right? It's just, the frame we're using, right? Now, how do I know how to get, so this x goes all the way up there, right? But how do I know that the y should be this instead of that? You see, because it could be either one, right? I need those parameters. Oh, I'm sorry. Sorry. So again, this equation, so if I give it x, is that, right? This line. Yeah. And given this x, I'm going to get a y, either this one or that one, correct? But how do I know that it'll be this y versus that y? Well, that's dependent on this line, right? Because this could be that line and this could be that line. Do you see that? All right. And so what determines this line? This line is determined by m and b. So this line will have an m1 and a b1, whereas this line will have an m2 and a b2. So that's another way of saying one line has one set of parameters, the other line has another set of parameters. And that very simple concept is all that happens in machine learning. Machine learning is about, you give it, so let me move to something less messy over here. So machine learning is about, let me draw this again. So I have F1, F2, I had my samples, S1, S2, S3. Additionally, I also learned, we know that mx plus b, this little equation, in a Cartesian plane, right? And I guess maybe to make it easier, F1, F2, right? That kind of should, mx plus b. This allows me to draw a line. So remember that the F1 or the X1 are these, right? They can be whatever. Any value in Y is correlated to any value in X. But the thing that determines that correlation is these parameters, M plus B. If I draw another set of M plus B, I get another line. Another set of M plus B, I get another line. Another set of M plus B, I get another line. Yes, sir?
Where are the M and B coming from?
Excellent question. Excellent question. So do you see that, right? So now we have, so let's just think of it this way. We now have a mechanism that allows us to draw lines. But that's your important question. These lines are not the line we're looking for, right? What is the line that we're looking for? We're looking for a line that separates the two classes, right? We had said that we have this, two classes, right? Oops, that's not what Wait, what happened? I may have lost that, I think. Okay, sorry. So I may have lost that. But anyway, so really quickly, S1, S2, S3, align y equal mx plus b. All right, so the question you asked is, where do these come from? Well, we know that they determine the shape, right? Now, the shape that we want, let's say, is that one, is a line that separates these three samples, right? These two, those two from the other ones. So these are the parameters, m plus b, which have to be learned. So when we talk about machine learning, believe it or not, that's all that the machine learning algorithm is doing, is learning these parameters. Do you see that? So they come, so to answer your question, where do they come from? They come from the fact that you give it data with labels, right? And then you give it an objective. And the objective is to find a line that best classifies the two samples. Does that make sense? So you figure out this m plus b by optimization. So you optimize the algorithm, you give it samples, it tries things. So that's what I was saying. So for instance, let's take one example. I give it one set of m plus b, and it draws this line, right? Now, with this line, I'm going to have how many errors? So if you remember, let me just 0x, x. Right? So that implies that everything to the right of this line is one class, everything to the other side of the line is one class. So how many errors will I have here? 1, right? So it's 66% accuracy, correct? Do you see that? So that's how the algorithm works. It's an iterative process. It's an iterative process, right? And so with this mechanism of building the line, you build a line. You apply this to a sample, and you plot it like that. And you say, okay, given this, how many errors do I get? I get 1. So what do you do again? Because it's an optimization, you repeat it. What do you change now? The slope, right? Somebody set the slope, the m and the b. You change it to another one. So what does that...
You know it's an error because you looked at it.
Yes, you know, because it's supervised learning. So the cycle is like that. You give it data. First you build a vector space model. You plot the samples. Then you want an objective of creating a line. We know how to create a line, but we want a line that when we apply it, it reduces the it improves the accuracy or reduces the error rate. Now in this example, it's not obvious because it's only a few. But let's, now that we understand this part, make this even more complex. Right? So now it's a little bit more obvious, right? If I draw that line, because I picked M1, B1, given my X and my Y, I built a line that looks like that, right? That's my solution at this point. I evaluate it. What would be the accuracy of this, would you say? It's not great, right? It certainly went down from 66% to, let's say, 50%. Do you see that? Okay. So what if I iterate again and I try this line? Is that a better line or a worse line? Slightly better, right? Because now you know, before you had one more error, now you have one fewer, right? Okay, next iteration. Better, right? Somebody said better. And then, let's say I draw this one, worst again. Okay, so I'm learning something. What about that one? Better, right? Until that one. You see that? That's the best one. The most, well, you can't even say the best one, but the most optimal. So after a whole bunch of M1s and B1s, you actually arrive at the optimal set of M1, B1s that create the best line that separates the data. That's the intuition of all of this with the vector space model. And believe it or not, from here all the way to deep learning, That's the same principle. Because now the equation won't always be this simple, right? We know that this is one feature, right? But when we have multiple features, we're going to rewrite this as, you know, W1 x1 plus W2 x2 dot 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 Wn xn. Do you see that? So that's where I was saying before that you have, you know, the Euclidean distance space, all of that, even though we can't visualize it in multiple dimensions, the math of it still holds. Right? The math of it still holds. And so creating these lines allow us to create these separators. And that's all a classifier is. In a Euclidean space, it is a line that we're learning. One last one, for instance, so I'm sure you've heard of linear regression. You know in linear regression that you don't have labels, but you have things like that. What is the objective in linear regression? Fit a line through that data, right? So if I fit this line, is that a good fit? No, right? That one? Nope. Even worse. How about that one? Much better. Do you see that? Pretty much the same mechanism. Only a slightly different objective. Whereas in linear regression, it's about fitting the data, right? In supervised learning, it's about learning on the position of the line which best separates the data. And we can think of it intuitively without knowing like the underlying powerful algorithm. We just know I drew that line. Now I apply it, measure the performance. If the performance is bad, guess what? Don't use that line. Use another one. Right? So the idea is that you give it enough samples. You can never give it the population, but you give it enough samples that it's going to learn basically the tendency of the data, right? And so you can assume that the line is going to get good eventually. Is this clear for everyone, guys? This is very important, actually, and this is the vector space model. So this gives you the reasoning why we want to create the vector space model, because then later we want to create this.
So is the M and the B adjustment done by me?
Hmm?
Is the adjustment for the M and the B done by me?
Oh,
Or
no.
done by the algorithm?
The algorithm. That's what's so
When
great
I
about
say,
it.
no, this is not a good line, or this is worse than last time,
Mhm.
it says, all right, I got to adjust. And it-
But that's what the machine learning algorithm does. It learns that because it's supervised learning. That's the trick. A human reviewed these things. This was a cat, this was a dog, and then you just built a line that best classifies them. Do you see? Yeah.
That's what the Y vector is.
The labels, yes.
The label.
Yes, the y vector is the labels. That is correct. So going back to his example, right? So this was the data that you plot, and these are the labels. So I think I understand your question. So the labels, how do we represent the labels in this plot? That's why I kept changing the color of my pen, because they're not actually an axis. They're really, that point is associated with a label, is what it predicts.
That's how you figure out the accuracy.
That's how you figure out the accuracy. That is correct. Yes. Any questions? As you will see actually, when we start doing this in TensorFlow, we will literally write these equations, and we will literally write like this y and this b, or this w and this b, which is the m and the b. All right, so we'll write that out, but the principle is this. So hopefully that makes sense. So I'll kind of summarize it. One more slide. I think it's very important. So again, remember, you take the features, that's the vector space model, you create F1, F2, F3, and possibly all the way, most likely, all the way to Fn. These are orthogonal, which means they're like 90 degrees, similar to how we understand it in 3 dimensions. That means that every instance, so every sample, so this is something I haven't said. In his example of the radio signals, which every sample was a 1-second interval, basically, this has F1, F2, F3, all the way to F35, I think he said. Remember, in this space, each one of these is what? A point. So it's just one point. Okay? So every sample is a point, another point, another point, another point. All right? In that space, whether it's so here in this three-dimensional space, right? F1 or like this and like that, right? So each of us is a point. Right? Each of us is a point, and so we have, you can measure the distance between, the two students there, right? You can calculate that. We can build a line in between here, right? That group and that group. Do you see that? It's your type of radio signal command and then another command. But if that changes to something else, right? The distance where the signal came from, I don't know, right? It might be that now it's the people in front versus the people in the back. But at the end of the day, we know that y equals mx plus b from school draws lines. All we have to adjust, the x's and the y's are just the positions, but the thing that changes, this line moving around here is the m and the b. And those are the things that the algorithm learns through something called gradient descent and things like that. So there are specific algorithms that are very deep, but because we have TensorFlow and things like that, we don't actually have to understand that, thankfully. Any questions? Does this make sense, guys? All right, good. So that's it. I mean, that's really it. If you understand that, again, the key is we did this exercise, we took a problem, right, and we identified the features. Once we identify the features, we create something like this, the vector space model, but this actually looks like that. And we want it to look like that because we have distances, we can draw lines and things. All right? All right, so no, I don't see any questions yet. So let me then just really quickly try to look at my slides. I'm sure I've said a lot of this, but I just want to see if I'm missing something. All right, so here I talked about data sets. I gave all these examples. This is just code. That's called slicing. It's something that we're going to do later. That's more of a practical thing in the code. There are reasons why we use linear algebra in Python, right? Did any of you ever use MATLAB? MATLAB? All right, MATLAB, right? So MATLAB is this environment where you do linear algebra operations, right? And then like 10 years ago, there was Python, but Python didn't have that ability to do those linear algebra operations. So they had to change that. So basically what we do now in Python is like what you were doing before in MATLAB, which was thinking of things as vectors and matrices and performing the operations in that environment. Right? So you'll see that in the code, everything will be a matrix or a vector, and we'll be doing, extracting information from those things. So that's called slicing. Don't worry about it yet. Let's see. This is just the Irs data set, right? You can see there it's got Y is the labels, and then X1, X2, X3, X4 are the features and some values. Kind of talked about that already. The data sets, these are some of the data sets that we're going to use. Don't worry about this. But there are many kinds of data sets, though. They can be text-based, radio-based. They can be images like cats and dogs, speech, similar to radios. I mean, I would argue, take something from the time domain to the frequency domain. NSL KDD, this is our network intrusion detection data set. We will use this one. It has about 41 features, and the samples are packets, although they could be time intervals as well, right? So it could be like all the packets in 1 second. That might be like 100 packets or so, right? So how do we process that? We'll have a big data intrusion detection example, and you'll see that there's nothing to it, really. Because once you understand TensorFlow, it could be small data, big data. It doesn't matter. It's the same thing. So really, the only thing that changes is that when you ran a big data set in your laptop, it crashed. Now in a big data environment, it'll run. But the algorithm is the same. And so that's a great advantage. The phishing, we'll do this one. This is more like text-based, URL-based. Unsupervised, we'll take a look at that as well. Malware, we will do an example of malware, of how that works. Fraud detection, this is another one, right? So this is another data set that's important because this reminds me of the issue of balanced and unbalanced data sets. Do you guys know what that is? Balanced and unbalanced? Can anyone give me like a answer?
Fraud, not fraud. So not
Fraud and not fraud, but in the context of unbalanced, what is that?
5% fraud, so you have enough to train on it, so you can synthetically do it or replace it.
Perfect. Exactly. So, and not even 5%, probably like 1%, right? And
From Chicago.
Yeah. So fraud detection, exactly. So usually when you do your machine learning, what do you want? You want to have an equal number of each class, right? A balanced data set. So 50 images of cats, 50 images of dogs, right? That's kind of what you want. With a fraud detection, you have 2% are fraud, 98% are not fraud. So think of the vector space model here. So think of the vector space, right? So now you have this, right? And you have, a huge amount of not fraud, right? And then you have a tiny amount of fraud there, right? Now think of your algorithm, and figuring out that line. It needs to figure out a line like that, right? In a perfect environment. And that's going to be more difficult because you have more examples of this than of this. So the algorithm will have a tendency to favor the majority class. Do you see that? So that's going to happen in this. So usually you have problems with this unless the features are really great. So what his answer was what?
So you can synthetically replace.
Synthetically replace.
Or just replace with. What's that called? Replacement.
Yeah, oversampling or undersampling, right? So what is he saying? So oversampling. Figure out the distribution of this one, and then start adding synthetic ones. So that means if the mean is here and the standard deviation is out to here, you start to create a whole bunch that behave sort of like that minority class. The other solution is undersample. Get rid of some of these and try to balance it out. Do you see that? But there are disadvantages to doing that because you're getting rid of information or you're adding synthetic data that wasn't even there. Do you see that? So all I want to say with this, with unbalanced and fraud detection, is that it creates problems, additional problems. But most real data sets might be like this. In network intrusion, do you think it's a balanced data set? What would you, or even better question, in your experience with data sets or problems, can you give me examples of situations where you thought the data was balanced versus imbalanced? Yes.
But prior to asking that question,
Yeah, go ahead.
could you take, just say for instance it was 98%, 2% here, start to divide these guys up into like sets of 10 and reduce down the sets and try to see if one particular model with just a certain amount of points would actually be able to predict those other two? As opposed to like,
I think I understand your question.
so say for instance
Yeah,
98 points. Instead of using it on 98, you just start exactly. You start doing
get rid of this one, get rid of that one.
or
Try.
not even that. Just take the entire cell at one particular point and see if that one particular cell can actually determine that from
So just one.
just one that entire one in the middle.
Yeah.
Like you was thinking of tic-tac-toe, that entire one in the middle, that one, and can you predict those from that one?
So build a model based on this and this alone, and then test it on the rest.
Exactly, and then keep doing that over and over and over again, and then try to see which one might be.
I don't know. That's your strategy.
Okay, cool. Well,
Yeah.
I'll talk with you about it.
You can totally try it. I mean, it's interesting. I don't know how it would do, but I actually think it's an interesting thing to do.
All right, and another one would be if you just picked ones from certain ones, just randomly pick points from each.
You
one.
break it up and then you pick a few from here, a few from here. Yep.
Exactly.
You can try that too. Yeah.
Okay.
Yes. I mean, I don't know to answer your question. It sounds like definitely something to try. Yeah. All right. So anyway, so imbalanced data sets. In conclusion to this, imbalanced data sets are a problem. And so you kind of have a tool set there of what to do. You provided 2 solutions, right? And they're just kind of like,
Yeah, I mean, it's actually in the problem I have.
yeah, they're just like, yeah, okay, you have imbalance, so oversample, undersample. Try his approach, it's very interesting, right? You already have 3 things. At the end of the day, how do you know that it worked? Because it's a supervised learning problem, right? And when you measure the performance of your algorithm, you will see, oh, this improved accuracy. So oversampling improved my accuracy from before. So remember, in machine learning, there is no proof. There is no math, algorithm or conclusion that you can make about things. It's all, at the end of the day, based on the performance of your algorithm. So that's why when you have more data, you feel more confident that you built a good model. So it's kind of like this example in the stock market, right? So if you build a model to predict stocks that make you rich, well, if at the end of the month you're poor, you lost your money, right? It didn't work. So rebuild your model. But if after a year of refining your model, you're finding that you're wealthier, then it's working. It's kind of like that, I would say. It depends on the performance of it at the end of the day.
But in the end,
Yeah, go ahead.
in the end, you're not trying to build a model against your training data. You're trying to build a model that will give it unknown data.
Oh, yeah. Exactly right. Exactly right. So the process involves, and we'll talk about this, splitting the data. So you're going to build out, a train set to train the model and a test set that when you have the model, you apply it to, and that's really where you measure the performance. You're right about that completely. Any other questions? All right, so let me just look over these slides. So that one, I wanted to mention that biometrics, this is like image processing. What are features? We already talked about that. Ways to represent a sample, the vector space model. Now, types of features can be binary or continuous. I think actually someone had a question similar to this. So usually they're numbers, right? So they can be either zeros and ones. So for instance, in natural language processing, right? If you're reading documents, the word "the," that appears a lot, right? So it's a 1. And then a word like azimuth, that probably doesn't appear a lot in sports-related articles. I don't know, it might. But you see that, so that's a 0, right? So it's kind of like that. You have that, so that's features. They can be binary or they can be continuous, like his examples of angles of 360, and other things. All right, so the features can be, however, they shouldn't be words. So if they're words like left, right, up, down, you want to encode those into 0, 1, 2, 3. And we'll learn about that in sklearn. There's something called the label encoder, which does that really easily. Dimensionality, we talked about this. So the number of features determines dimensionality. So I think we've stressed this quite a bit. So I already talked about supervised and unsupervised. With supervised approaches, the learning methodologies can be divided based on whether they predict a class or a magnitude, right? So for instance, what we were doing, intrusion, not intrusion, that's a class. But a magnitude is an example of linear regression, right? So in linear regression, housing prices, square footage, other things determines the price, right? And that's a real valued number. An additional categorization is sequential versus non-sequential. So everything we've done is sequential. Non-sequential would be something like this, the classic example in something called hidden Markov models. So I want to predict ice cream consumption this week, right? So every day. So ice cream, no ice cream, no ice cream, ice cream. So I'm not trying to predict just is it ice cream or not ice cream. I'm trying to predict in one shot for the week, for this week, I'm going to consume ice cream today, followed by ice cream on Tuesday, but then no ice cream on Wednesday, no ice cream on Thursday, and then ice cream again on Friday. And so to predict those labels, the inputs are sunny, sunny, rainy, rainy, sunny. You see that relationship? So that's what is called sequential data analysis. There's 2 techniques for that. In the traditional sense, hidden Markov models, in the deep learning says something called recurrent neural networks. And so that's the difference there. We're not, unfortunately, time does not permit for us to cover this topic in the class. However, if you have an interest in it, just let me know. I can give you some references for it. But the principle is that. I don't know what examples challenges you might have in that. But it's really like that. Your observations are sequential and dependent, and so they're conditional. So this one depends on the previous one. So it's like the one on Friday is actually dependent on the one on Thursday, Wednesday, Monday, and Tuesday. You can model that, and it'll give you the predictions for, as I said, ice cream, no ice cream, no ice cream, ice cream. All right, so that's one categorization of machine learning. This, you can just read through this. This is just a table I have of the different algorithms and some definition, pros and cons. All right, so we're not gonna cover all of these, but this is an example of some of them. What are the machine learning algorithms that are out there? There's many. We have support vector machines, which is really popular. Used to be the most powerful one just before deep learning. And then we have traditional ones like naive Bayes, decision trees, random forests, and k-nearest neighbor. So I will definitely discuss k-nearest neighbor. We will use decision trees and random forests, naive Bayes, and then of course when we do TensorFlow, we will do this. All right, so these are just different algorithms. So support vector machines, just to give you a quick example. Support vector machines, right? Just intuition, but just so you understand. I have this like that, and then I have that. Which line, so this line works, right? And this line also works, correct? And that line also works. But of those three, given that this gets pretty close to where you might almost have that, which of the three would you say is the optimal one? Which one? The middle one, right? Intuitively, we just know. We just know that intuitively, that the middle one, because we feel that is safer somehow, right? There's a little boundary there because it's in the middle. And so that's what support vector machines does, is that it, instead of calculating one line, think of it as calculating a rectangle, right? So it fits a bigger line, and so when you have less flexibility to move it. Whereas the other lines kind of moved a lot. Here, you're going to hit something if you start moving it. So it provides a more optimal line, if that makes sense. Do you see that? So believe it or not, that's all support vector machines did, right? Or kind of. There's like another thing that it did. But that really essentially is it. Support vector machines, that algorithm just took the whole fitting of the line a step further by adding those boundaries to the left and to the right of it and creating just a slightly more optimal solution. All right, so that kind of gives you an idea of the differences. This one is based on probability theory. All right, oops. So it's probabilistic, right? And these are the neural networks, deep neural networks, right? And these are kind of like heuristics, like rules, if statements, right? That the algorithm learns, the decision trees. All right, so anyway, there's few differences. We will cover this a little bit more, especially on Tuesday, all right? The difference between the algorithms. Deep learning, we'll spend enough time on this on Wednesday, so don't worry about it for today. Feature engineering, this is the experts, right? Coming in and figuring out what are the features that we need to use. So for instance, let's go back to his speech processing. Or signal processing. So this is the time, this is the frequency, correct? And this is the signal. But, from like math, we know that a signal in the frequency domain, or the time domain, can be converted into something in the frequency domain. So that just means that we take the signal, apply some function, right, to it, and transform it into something else. So a lot of people, before deep learning, for instance, spend a lot of time just doing this. Figuring out these very fancy equations and things like that. And so that's feature engineering, is creating all of these features. All right? Questions about that? All right, so it's just your expertise, right, of creating something. So for instance, I don't know, some of you may be experts in some type of cybersecurity problem that I don't know about, but you know what the features are for that. You know what you look at, right? You know, if you look at SQL injections, right? You're looking for a SQL type of code, or you're looking for buffer overflows. What are we usually looking for there? The shell code, right? You know, the hexadecimal type of code that's in there. And so machine code. And so you know about that. And so that's what feature engineering is. Okay? We're going to learn a lot of libraries as we start coding. And sklearn is one of our libraries that we will learn about, so don't worry about this slide. This just kind of describes what it is. It's the main library, which contains most of the traditional machine learning algorithms. We will use sklearn actually to do a lot of the pre-processing, including, somebody asked me about train and test sets, right? We will do that here. We will split our data. So here, hold on. I think I have some code here. Yeah, there it is. So we have this function, train test split, and this function takes that x and the y. We specify that we want to, for instance, do a 30% split. And so it'll start to produce an x train, an x test, a y train, and a y test that contain the data that we need. So we'll do a lot of this later as well. Now, somebody asked me a question about processing the data and cleaning the data. So one thing that we will do is to normalize the data. And normalizing the data is, for instance, if you have port numbers. Just let's take this example. From 0, how many port numbers do we have? 65,000 or so, right? 65? All right. That's the scale of that access. But what about protocols? Common protocols might be from 0 to 20, right? So really does this graph look like this? Not really. Instead, this graph looks, don't you agree? A little bit like that? The space where you plot this data? Do you think that's good for a machine learning algorithm? Probably not, right? You want to kind of have equal sizes. So you want to actually have that there, right? So what we're going to do is something called normalization, which allows you to basically take this and convert it into a range from 0 to 1, 0 to 1 for every access. And that may improve your results. Does that make sense? Okay. Yes, sir?
It's also normalized based on the variance or the standard deviation.
It's going to be based on some algorithm. You're right. So we're not going to get into the math of it. We are literally just going to use the most optimal function that we have in sklearn to transform the data. And sklearn and TensorFlow will be able, you could choose another one that's more optimal, for instance. But you're right about some statistical method will be used with this function to normalize the data. All right? Okay, so that's one thing that's part of the process, normalization. We'll do this in the code every time. All right? This is just an example of calling the function, so don't worry about that. All right, so let's switch it up a little bit. So now that we've covered a lot of theory, I think we've covered quite a bit, right? You know, vector space. We're going to do, so let's go back to the schedule. All right, so you can see here, you know, I kind of gave the introduction, and I kind of did the lecture on data sets and features. So the next thing I want to do is now just complete the pipeline, right? We're going to complete the pipeline. We have about 40 minutes, so I think we should be able to do it. So Tingyu, the Irs Data Set is in the flash drive, correct? Yeah. Right? Yeah. So what we're going to do now is we're going to start up the computer, right? We're going to start up the computer. We're going to use VMware, so you know we'll take it slow, right? But you'll take your flash drive, start up VMware, start up the VM, right? And then we're just going to, or actually, is Weka in the VM? Weka is not in the VM?
It's on the system.
It's on the system, right? So just use Windows then?
Yeah.
Okay, so the Iris is not in the VM, it's also in the flash drive? Okay, so we'll do that then. Even easier. Let's just start up Windows. Can I get one of those flash drives? All right, so let's use the flash drive. So we're going to kind of practice some of the things we've talked about. And that way you can do some machine learning on your first morning, right? So, so let's log in. So, all right, so it's this one, right? The Iris. All right, so go to the flash drive, Samsung USB, right? And then in Code and Datasets, double click on that, and this is basically where our datasets are and things like that. So go to Iris. This is that dataset about plants that I was talking about. All right, open it. Click on Iris. You can copy it or run it from there. Oh, remember these computers are.
What letter is the drive?
Sorry, sir.
What letter?
Oh,
I think it's the
yeah, it should be this one, D.
Only USB drive you have, probably.
Samsung USB D. Do you see it?
You might have to push your drive in harder. Mine wasn't showing up at first.
Tingyu, can you help me? If you have questions, just raise your hand, so we'll help you. It's him in the back, the blue shirt. Okay, everyone else with me? All right. Oh. Yeah, so this is the Iris data set that we're going to try to use. So we can double click on it. And as you can see, it's really, the format is something called a comma separated file. So it's CSV. You can see here, what are the things that we have in this data set? Well, each row is a sample, so it represents a plant, right? So each one of these is a plant. What are the features? They're sepal length, sepal width, petal length, petal width, right? So those 4 features are what represents each plant. Notice that we don't have any missing data, right? Very important. Everything has a value because that's what the algorithm is learning, is the differences between these features. And then the label is here at the end. The heading is called class, and we have Iris setosa, versicolor, and virginica. So these are 3 classes. This is a 3-class problem. All right, good. So if we were thinking of his radio signal problem, we would want to do all the conversions to arrive at this. Pretty much, whenever you do your problem, whatever it is, you want to put it in the vector space model. Because the great thing about this is once it's here, just remember this, it'll run in Weka in seconds. If it's really large, okay, then apply TensorFlow. Because TensorFlow has other properties. For big data, for instance, it doesn't need to read all the data at once. You see, it'll run a little batch, then another batch, another little batch, and so on. And so it's built that way, very efficient. All right, any questions? All right, so this is our data set. Now, so Weka is here, correct? Huh? We are using the Windows system on your physical machine, right? All right, so Weka 3.8, I'm going to click on it. You can ignore this. You just click OK. So everyone here, you got this? Okay, great. So you got this little window. I should say Weka is from the University of Waikato in New Zealand. They were one of the first to make machine learning available to the masses, if you will. Before, it used to be like just people writing their own code, and then they created this tool set. It's very good. It's actually, as I said, a data set of 100,000 samples by 10,000 columns will run on a laptop with 8 RAM. So even if your data is millions, you can always just take a subset of that, load it here, get a feel for it, right? And that's what this provides. It's like a prototyping tool, I would say. So I think it's really nice. Anyway, so it's got 5 buttons, 5 main buttons. We can ignore these 3, and really these 2 are the important ones. So the Explorer is mainly where you explore the data, right? Explore the algorithms, get a feel for it. Experimenter is for people that are statisticians, I would say, or math people. That because, you know, what the Explorer will do is it'll say, well, I think algorithm naive Bayes is better than algorithm logistic regression. But a statistician might say, but do you have a t-test, right, to corroborate that? Because that's how statisticians are. So if you want that information, you use the experimenter. The experimenter will allow you to do t-tests on the algorithms to provide confidence. I'm confident that this algorithm is better. All right, but for now, you rarely need this. So let's just look at the Explorer. So let's go ahead. We're going to open. We're going to navigate to Samsung USB, Code and Datasets, Iris, and down here, it's a CSV file. So it by default, Weka uses a file format called ARF, but we can just say all files. Do you see that? And now the file that you need, iris.csv, is there. So you can click on it, open it, and there you go. Did everyone get here? If you get stuck, you just raise your hand. We'll help you. Okay. All right. So why is Weka an interesting tool? Well, because it allows me to look at my data really quickly, right? So what do I know here? I know these are my features. I can look at the distribution of the data, right? Like, okay, this is how things are distributed, like histograms. So this is a histogram of that, histogram of this feature, and so on. The labels, what do you see here? There's 3 labels. They're balanced. I know that immediately. These are the labels, Setosa, Virginica, 50 of each. Very important, the data type. This is a nominal feature, whereas these are numeric. If I want to see the data itself, I can just click on Edit. Click on Edit, and you can see it here. Here are the samples, right? Here are the values. Here are the labels. Okay? So whenever you want to do supervised learning, you want the class to be nominal. So this is something that sometimes might appear as numeric. So you need to change it. Right? We'll have other data sets where we have to do that. So don't worry about that yet. As I said, for our purposes, this is perfect. So we don't need to do much. This also tells us that there's 150 instances. Right? There's 150 instances here. Now, I want to do machine learning, right? So the data's already loaded, so I'm going to go to Classify. And here in Classify, I can select an algorithm. So for instance, I'm going to select naive Bayes. I always like to start with naive Bayes because naive Bayes is one of the fastest algorithms. It usually provides the lowest accuracy or performance, so it doesn't learn as well. But that also means that it sets a baseline. So that indicates that any other algorithm will probably do better than naive Bayes. So that's very helpful. So click on naive Bayes. All right. Now, additionally, remember, we just loaded one data set, right? One data set of 150 samples. 3 classes each. So, but as someone had said, whenever you train a model, you train it on the train set and then you test it on the test set, right? So we need to do a percentage split. This will be done randomly. So we just say we want a 66 or a 70. 70% split, right? So 70% split means what? It means that,
Don't say anything. it's your test set and your training set.
That's right, that's right. So the test set randomly contains now 30% of the samples, and the train set contains randomly 70% of the samples. Do you see that? Now there's something else called cross-validation. Anyone know what that means, cross-validation? Yes, sir.
You fit it n k times, like where k is the number of folds, and you leave at each time one of the folds is the test and the rest are training.
Exactly. And why is that better, do you think? Or worse?
Assess the accuracy of all items.
That's right, because it could happen that for whatever reason, the samples are in order somehow. You know, it's like whenever you're looking at healthcare data, right? So it might be bunch of lab tests, but they might have it by patient. So patient 1, 10 tests, and then patient 2, 10 tests. And so what happens there? You know, there's some correlation for patient 1, right? It's the same person. And so what happens is, you know, you might have in that 70% some patients, and in that other 30% you might have other patients that you never saw in the train set. You see that? So randomization alone may not work, and that's why you do the tenfold cross-validation. Now you're testing down here, up here, you know, so you do what he said. You leave one out, exactly. Divide the data into 10 bins of equal size, do 10 iterations. Every iteration, leave one of the bins out for test and use the rest for training. All right? But let's not do cross-validation yet. Let's just do percentage split. We pick naive Bayes. Now, if you wanted to change the parameters, you could click here and change the parameters. But for most of these, after 15 years of this, you know, the default values are good enough. All right? Remember, it's just a prototyping thing. This is actually, as I said, setting your baseline only. The other thing you need is to select the target class. Do you see that one here? So that's what the thing that you're trying to predict. So you make sure you've clicked on that, and then hit start. And that's it. Very, very easy. You see that? So what is the pipeline in data science? Understand what it is that you're trying to do, your radio signals, whatever that is. All right? You need to figure that out. Find your raw data. Is it supervised or unsupervised? Do you have the labels? Can you trust the labels? Convert your raw data to the vector space model. We talked a lot about it, right? That little Cartesian graph. And once you have it in the vector space model, it looks like Iris. Load it into Weka. That's your first step right there. And you get some results. Now, I haven't interpreted the results, obviously. I just showed you all these numbers, right? But you have to interpret them. And this is what's called the performance metric. So if you care about the math, I will cover the math of it on Tuesday. So here, I'll cover the math of it in these, or you can start reading or look at the video as soon as you want. But we need to interpret what we see. Remember, we can't visualize it. It has 4 features, so we can't actually like plot it or anything, you know, 4 dimensions unless we compressed it. But we don't want to do that. Instead, you don't want to get into that habit. Instead, you want to learn how to interpret this, right? Now, because we can't see it, we need to have actually more than one feature. So we actually have several, or more than one performance metric. So we actually have several. We have accuracy. We have something called precision. We have something called recall. We have something called the F measure. And we have something called the confusion matrix. So these are the main 5 metrics that you can use to evaluate this. As I said, the equations and everything I'll discuss on Tuesday. So I'm not really going to say today what's the difference between recall and precision.
You also evaluate on probability, like if you like score it like we're based on the probability that it's in the actual class.
Logistic regression actually does that. The algorithm, logistic regression, it basically says it's this class with a 70% probability.
And it gives a score of like log 0.7 for that.
Yes.
I mean, so one that.
But that is logistic regression only.
Whose probability is 51% wouldn't score all that much higher than one whose probability is 49%. But in like the straight classification algorithm, one that has a score of 51% for the actual class is
Okay.
And this kind where you're just using yes, no for each class.
True, and that's, I think, what you define as logistic regression is a type of an algorithm. This is a little bit different. So accuracy, straight up accuracy is what? You have 100 samples. We've done it already, right? 100 samples in your test set. And 60% of those were correctly classified and 40 were incorrectly classified. So that is 60% accuracy. That's it. There's nothing of probability or anything like that. It's just look at, counting. Exactly. Just count. That's ultimately what this is. Remember, so I think I've said this before a few times. So machine learning loosely uses math and loosely uses probability theory and things like that, right? So it's sometimes a little bit more about counting and measuring the results. So that's why it's data-driven, right? And it's just about things like that. But as I said, I guess just really quickly, since some of you have, I can see in your faces, I will cover this tomorrow, but these are the equations, right? So all of these are, the accuracy, right, is just of all how many were correctly classified. And then we can look at things like precision, recall, and the F measure, right? They're all the relationship. All right, but we'll see that tomorrow. Anyway, so let's analyze this now, just not of how we interpret the data. So precision. Notice also that this shows the data per category, right? So it shows it overall, that's the fourth line, and then it shows it for Setosa, versicolor, and virginica. So it's telling us that the precision is 100%, 88%, 100%, and 96%. So it actually tells us that it finds versicolor the hardest to distinguish. Right? It finds versicolor the hardest to distinguish. So these are the metrics. So basically what you would usually want is you would want these to be high numbers, right? That's really ultimately what it is. If I'm doing like I want to publish a paper on something, I actually don't want this to say 100%. Because what does that tell people if all my values are 100%? What do you think? As a reviewer, what would you say?
Not real life.
It's not real life. Well, this is too easy, So that 100% kind of tells you is very easy. Yes, sir.
But you might want to tell them what's a good range for publishing a paper in certain things. Because if you had a model that was actually 0.70, that's passing, but that may not be good.
That's true.
But if you have something that's 100, then you know that's not right. So as a result, something like maybe in the 80s or maybe...
And that's intuitively the way that I always think. It's like, oh, this is 85. Okay, it's not people will interpret this as not being too easy and also not being too poor. The algorithm did okay. Do you guys see that? And so that's really forget about the equations for now. Just think about interpreting these numbers, right? So this is Iris. Obviously, it's the most academically used data set, right? It's perfect for just the first machine learning data set. But it tells you a little bit. Classifying versicolor was a little bit harder in the precision. But in the recall, it was easy. You see that? So there's an interpretation there, what we will learn later. What is the difference between precision and recall? Accuracy was 95 overall. F measure, this is usually the one metric that we look at. And so here, they're all above 85, so they're all good. That's what I would conclude. Now, the last one, which is actually really important, because all of these are based on this, is the confusion matrix. And that basically, I'm sure just by looking at it, you kind of already know what it means, right? It means that out of all the ones that were A, how many were actually correctly classified as A? So what would your answer be for that there? All of them, right? Perfect. But what about for the second one? Were there any misclassifications for B? None, right? And then for the last one, there were 2 misclassifications. So that tells you already that sometimes when it sees a C sample, it thinks it could be a B. So there's some confusion there. And so the confusion matrix is actually really useful.
But that's also 2 times it messed up.
Sure.
Never- never-
Sure, you're right. Right. So those are based on that type of information. You're right. All right. That's pretty much the pipeline. We're done. But that's why it's good to do Weka first. Is because it gets you really quickly going, even with somewhat large data sets. One more thing. Going back to someone said temperature as a feature that's not useful. You were kind of confused about your features. Have you done any feature ranking yet on your data set?
Yes.
Okay, great. So feature ranking is basically selecting the features. So actually this has selected attributes. All right, and what you do here is you select what you want to do. So search method, I'm just going to say rank. So I usually use this ranker. And then it actually suggests what technique to use. So if you care about the statistics, there's something called chi-square and information gain. Right? So that's like the math of it. I'm not going to get into that, but usually it's one of those two. So let's just say yes, and it's going to use information gain as the statistical method that it uses to figure out the rankings. Weka does that for you. What's really powerful about this is that it's going to make sure you select the class, and you can either do cross-validation or full training set. So now we hit start, and there you go. Now what's so great about this is that it ranks them. So now it's telling me that for this problem, to determine between setosa virginica or versicolor, the best feature out of F1, F2, F3, and F4, the best feature is petal length, which are 1.41. Notice the difference between the first one and the fourth one. The fourth one is getting close to 0. Usually, if these values are 0, then you just you can get rid of them. So that might be like the example of temperature that someone mentioned. So that temperature, if it had a 0 there, get rid of it. Because it's actually, if you leave it there, the algorithm might get more confused. And so just don't have it. So this is feature ranking, and this is very important. Let's say that you were doing like analyzing what are the features that help you to distinguish between malware and goodware, right? Again, do this. And it might say DLL calls and registry edits and things like that are important versus other things. Questions? Yes, sir.
So, I think
Yeah.
there's a model now that can classify unclassified data. It's in the same.
Can classify what data?
Yeah. So how do I use this now? If I've got a second spreadsheet that has
Oh.
but it's unclassified. How
Yes.
do I make the model tell me what is the classification?
Perfect question. So you're saying a train test and a test set, right? We actually have a lab for this on Friday. It's this one, small, KDD small. So how do you do that? That's a good question. So let's go here. So here you load the train set, right? Just like we did. But you have a second file called the test set. So then you go here. It's a little like odd how they do it, but this is how it works. So what you will say is, instead of selecting percentage split or cross-validation, you will select use training set. All right? Then you do the same thing. You select class, hit start. There it is. This second entry is all based on that as a train set. Right? You've created this model. That's the model that you're going to apply now to your test set. So what you would do now is you would click on this, which says supply test set. You would click set, and this allows you to find the file. So then I would say open file, and I look for my test set. Load it there. Obviously, they need to be formatted properly. That's why we have a lab for it. Once that's done, you come down here and you right-click this, and now you select this option. Reapply this model's configuration. Does that make sense?
And then it will spit out.
Then it will spit out this again, but only for that test set, that the model was applied to the test set.
And it'll have column E, which was blank,
Oh, you want the actual predictions.
Yeah.
I see what you're asking, not the performance metrics. The actual, in Weka, you can do it. In all other,
If I'm going off base, just
no. In all algorithms, you can do it. Obviously, it's just that in the other ones, it's more obvious. In sklearn and in Weka, because this is a GUI interface, I believe you have to. That's a question. That's a very good question that I actually haven't done in a while. I think it's more options. Output predictions. Here it is. So output predictions as plain text CSV. So So I will add this to the lab. Actually, that's a good. But it's this one. Output prediction.
Think about my problem
Yep.
at work. If I train a model, you need to be able to apply it.
Yeah, no, I completely understand. And sklearn, straightforward, will do that. TensorFlow will straightforward do that. Here, because it's a GUI, I kind of, but I haven't done this in so long in Weka, but it can be done. Yeah, no problem. And it's just basically this, specifying, I think you specify the path here where you want the file to go. I'll look into this again, but I'm sure it can be done, as I remember. All right. Any other questions about Weka? Yeah.
Can
Yeah.
Weka let you change your risk function?
Hmm?
Can Weka let you change your risk function?
The objective function? Can you change the objective function? I think if you go to the Java code itself, like the source code, you can. However, in TensorFlow, one of the things, that's what's so great about it, is that we will do the inference, which is the equation, y equal m. Let's think of linear regression, right? So the inference is predicting that function, but then you have another function called the loss function, which will be least squared errors. Is that what you mean? Changing that to some other function?
Well, yeah, your loss is incorporating whatever risks. I'm assuming Weka is incorporating equal risk for all of your values.
Yeah.
For example, if I'm
so you
treating cancer or something like that, like you have.
so you want to add weights maybe or something like that?
Yeah.
You can do that. You just have to play with the parameters a little bit. So it would be, let's see. Let me. So here's all the explanations of it and the capabilities. So like class attributes. So weights, instances, handler. So let's see. Let's pick multi-layer. See, all of this is here. You see that? So these are parameters that tie back to those loss function equations, for instance. So you can tweak the parameters a little bit. You just have to, what you can do is you read the, so which algorithm would you be using?
So let's do naive Bayes, since that's the simplest.
Okay, naive Bayes. Okay, so naive Bayes is probabilistic. So it's not necessarily a loss function. It's just a count of things. Like calculating frequency. So usually what it'll do is it'll tell you the parameters that you can change here. So I would say this one may not have that, but let's do logistic regression actually. So I'm trying to think where I've seen that. See, for instance, this is a cost in the objective function. So I know that for a fact because this is support vector machines. And so in the loss function, there's like, do you mean like the regularization parameters?
So when you have a loss function.
A loss function plus regularization maybe?
Like you're weighting, so you're weighting
Yeah.
your risk classification errors, which is like for SVMs, you have a cost of risk classification.
Yes, weight 1, weight for the classes, right? I know I've seen this before.
And we can talk offline too.
Okay, yeah. But this would be it. So just to kind of answer sort of your question, that loss function, I believe, is the loss plus a regularization parameter. That's times C. And so that C is really this parameter that you can set here. So that would be how you approach this. Through the GUI, you change these. That's the only thing you can change in Weka, is these parameters for each algorithm, unless you choose to go into the source code itself. But in that sense, you would be better off with, it sounds like what you want to do, you're better off with TensorFlow, which literally you write out everything.
Right, so like for cyber applications, for example,
Mm-hmm.
much bigger loss if you have an attack versus a false alarm. So you have like your loss function is not balanced.
So you're saying not using the standard loss functions, but modifying them to your problem. Okay. So you can do that with TensorFlow. Actually, the recommended thing is to use the built-in functions, but you can do that. Just because they might be a little less, unless you're really good at math, and you might run into some problems that it doesn't converge and things like that. You know what I mean? So, but otherwise, you can make the changes. So maybe if I look at your problem a little bit, whatever your equation looks like might, jog my memory a little bit. All right. Any other questions? Good questions, right? So very advanced questions. So anything else, guys? So we have 5 minutes until lunch, so I won't stand between you and your lunch for sure. So let's save the quiz for at the end of today, 4:30 to 5, I think. Just keep in mind, it'll be something like what we were doing. I will ask you to create the vector space model. There's no grades here or anything like that. All right, so I think I've discussed everything. You might say that there's other tabs here. I didn't really talk about them, like clustering, because I rarely use clustering here in Weka. Instead, we'll use sklearn for it. Weka really does everything that sklearn does and TensorFlow does. It's just that because this is GUI, we didn't code anything, right? So that allows us to get to our results faster. So it's a great prototyping tool. We'll certainly do a few labs. I didn't do other algorithms, so let me just do one more. So I'm going to do cross-validation. And so the algorithms I usually pick are naive Bayes, logistic, multi-layer perceptron, although this is a neural network. And this will be very slow in Weka. I've assigned homeworks to my students sometimes, and they tell me that they left it running overnight, and it's still running. So you don't want that. All right, so whenever you want to do a multi-layer perceptron or a neural network, TensorFlow is your way to go. Okay? But the logistic one certainly, lazy is, IBK is KNN, so that will be the KNN algorithm. It's a good one to apply. So for your, when we do labs, this is what you'll be doing. So, selecting a few of these and then comparing the results. Then you do decision trees. So let's say, for instance, I do J48 is decision trees, right? I apply that, and now I got results. So usually what you do is you look at this F measure, and then you compare it to the naive Bayes F measure. And then you say, so for instance, 95 versus 96. So you could argue that the decision tree does better by 1 percentage point. Kind of like that. Is it statistically significant? Only the t-test can tell us that with the experimenter. All right. So it's 11:58. Let's stop here.